Welcome to Easy Learn. Today, we're unpacking a total game changer in Earth observation, the TRISHNA mission. Now, if you're in the remote sensing or geospatial world, you know that mapping the Earth's thermal domain has historically meant making some pretty heavy compromises. But, as we're about to see, TRISHNA is designed to completely flip the script on global-scale thermal monitoring. Okay, let's jump right into this explainer. We're going to start by looking at the mission's macro-level partnership, break down the actual anatomy of the satellite, dive into the core science of surface temperature and emissivity, and finally, look at how this data will help solve some very real-world climate problems.
So, Section 1, the dawn of TRISHNA. Let's talk about the launch and how this whole thing came together to fill a massive gap in continuous, high-resolution thermal data. You know, this mission is actually a monumental team-up between India's ISRO and France's CNES, really bringing out the absolute best of both world-leading space agencies. ISRO is stepping up with the robust IRS-class satellite platform and the Visible and Shortwave Infrared Instrument, or VSWIR. On the flip side, CNES brings their unparalleled expertise in thermal observation to the table with a highly advanced thermal infrared payload. It's just a brilliant synergy of international engineering.
Looking at the mission architecture, we're expecting a launch aboard an Indian PSLV rocket right out of Sriharikota. It'll be injected into a 761-kilometer polar-phased sun-synchronous orbit, kicking off a 5-year baseline mission. And here's a really cool detail. That specific altitude and orbit, they were mathematically selected to minimize hotspot directional anisotropy. In plain English, that basically prevents distorting shadows and weird sun angles from skewing our thermal data.
All right, moving on to Section 2, let's crack this thing open and look at the anatomy of the satellite's dual instrument payload.
If you take away just one number from this explainer, make it this one, 57 meters. TRISHNA is going to deliver a 57-meter spatial resolution at nadir. That is a massive radiometric upgrade from legacy systems that map at 1-kilometer scales. I mean, think about it. Getting down to roughly 50 meters means we aren't just taking the temperature of an entire continent anymore. We're checking the fever of a specific city block, an individual farm plot, or a precise ocean current.
The thermal infrared payload developed by CNES is an absolute engineering marvel. It uses a 3-mirror anastigmat telescope to capture 4 distinct thermal bands, and it does this with a crazy precise radiometric accuracy of 0.3 Kelvin at 300 Kelvin. This kind of extreme sensitivity means it can detect the absolute subtlest temperature shifts on the Earth's surface, whether it's day or night.
And to back up that thermal data, ISRO's Visible and Shortwave Infrared Instrument grabs 6 optical bands, all perfectly aligned to measure things like vegetation, coastal sediments, and cloud cover. The green, red, and near-infrared bands are your go-tos for tracking vegetation health, right? Meanwhile, the blue and cirrus bands have a very specific job. They hunt for low, thin clouds to make absolutely sure the thermal readings underneath them are processed accurately.
Now, despite zeroing in with such high resolution, TRISHNA still manages a massive 1026-kilometer swath width, bringing its global revisit time down to just 3 days. 3 days! For 57-meter thermal imagery, that kind of temporal resolution is phenomenal. During its 8-day orbit cycle, it actually passes over the exact same spot 3 times from different viewing angles. That gives us a level of consistency that's honestly virtually unheard of for this much detail.
Okay, so we've got the hardware specs down. Now let's jump into Section 3 and look at the core science, how TRISHNA is completely revolutionizing LSC and LSE.
For the remote sensing pros tuning in, you already know that accurate land surface temperature and land surface emissivity are the absolute fundamental variables for figuring out the Earth's energy budget. They are the bedrock metrics we use to calculate exactly how much energy is being absorbed, reflected, and used across the whole soil-plant-atmosphere interface.
Historically, scientists have been stuck making a really frustrating choice. Do you want the high revisit frequency of MODIS or the high spatial resolution of Landsat? If you needed daily data, you settled for blocky 1-kilometer pixels. But if you needed sharp 100-meter pixels, you had to wait 16 long days and just cross your fingers that it wasn't cloudy when the satellite flew over. TRISHNA absolutely shatters this compromise, finally giving us that 57-meter resolution every 3 days.
Now, you might be wondering, why is it so scientifically crucial to cram these specific optical and thermal bands onto the exact same satellite platform? Like, why not just fly 2 different satellites in a constellation? Well, it's because combining them is what enables highly accurate split-window algorithms and radiative transfer modeling in a single pass. By capturing everything at the exact same millisecond, scientists can use the optical data to mask out clouds and map surface albedo. Then they use the 10 and 11 micrometer thermal bands for atmospheric correction. Finally, they use the 8 and 9 micrometer bands to actually separate the temperature from the emissivity. Nailing all of this simultaneously is basically the holy grail of thermal remote sensing.
And as you'll see in the foundational manuscripts published by the ISRO and CNES scientific teams, these radiometric improvements are exactly what fills that historical gap in continuous thermal monitoring. It's rigorous, peer-reviewed science ensuring that the Level 2 and Level 3 data products are going to be robust, incredibly reliable, and perfectly suited for critical climate modeling.
All right, let's head into our fourth and final section and talk about global applications and how this highly technical data actually helps us solve world problems.
Think about precision agriculture. By estimating evapotranspiration down to the scale of individual farming plots, TRISHNA is going to be a total game changer. It allows for incredibly strict water stress monitoring and helps optimize irrigation on a global scale. Keep in mind, agriculture eats up about 70% of global water consumption. So if we can measure exactly how much water crops are literally sweating into the atmosphere at a 57-meter scale, we can massively improve crop yield forecasts and help secure the global food supply.
But it goes way beyond the farm. Those 57-meter pixels will let city planners map out urban heat islands block by block, which is absolutely crucial for designing greener, cooler cities. Coastal ecologists are going to be able to track sub-mesoscale hydrodynamics, things like thermal plumes and harmful algae blooms. The data even penetrates down to the solid Earth and the cryosphere, meaning geologists can map underground peat fires and hydrologists can track vital snowmelt runoff in critical regions like the Himalayas. Ultimately, as the mission teams point out, TRISHNA will deliver innovative products for water resource management that enlighten decision-making at every single level, from a local farmer all the way up to huge institutions. It takes remote sensing from being just a cool observational science and turns it into a direct, actionable tool for human survival and sustainability.
These insights all come straight from the official ISRO, CNES, and HAL open science roadmaps we've used as our sources for this explainer. TRISHNA is truly poised to change how we view our world. Which leaves us with one final thought to chew on. Once this mission starts scanning the Earth every 3 days, what hidden thermal anomalies in your own region will it finally reveal?